Actually,
You didn't look nervous.
are you sure?
Yeah, I'm sure.
That's helpful. Same. From the come. You can.
Okay. Let me say a couple words about the next homework. I think this one will be pretty short, I think. Number one, consider the field extension Q inside QX, where that's rational functions of variable X. So this is like a transcendental extension. So QX squared and QX cubed are fields in between these, right? They're intermediate fields. Show that QX squared is actually closed, but QX cubed is not closed. Number two, we're going to focus on quadratic extensions. Suppose that you have an extension f of k that's of degree 2. Show that if the characteristic of k is not 2 and the extension is of degree 2, then f is always Galois over k. By the way, it's exactly in this case, that is, when characteristic is not 2, that you can use the quadratic formula. Number 2b, give an example of a field extension k inside f of degree 2, such that the characteristic of k is 2 and f is not Galois. Okay. And finally, give an example of a field extension of degree 2 in characteristic 2, where f is Galois over k. So characteristic 2 is like Wednesday on Mickey Mouse Club. It's anything can happen day. It depends. So, and finally, number 3, if E is Galois over K and F is Galois over E, is it true that F is Galois over K? Now, if you know anything about problem psychology, the answer is probably no, right? But see if you can either prove this is true or give me a counter. Okay, any questions? So let me briefly say something about what we were going over last time. So we had 8 to 10, and I'll kind of catch up where we are. So the situation here is we had this extension of the tower of fields. If the degree of M over L is finite, then the index of M prime and L prime is less than or equal to M L. And in particular, the degree of the extension F over K is finite, then the order of the Galois group is less than or equal to. So where we were last time is we were going by induction on N, which was the degree of the extension M of L. And the case for one is, if you just look at the definitions here, is clear. And so we wanted to reduce to a simpler case. We did that, and we reduced simpler case in the following sense. We selected if this group is bigger than one, we selected a U. M, but not an L. And since this degree is bigger than one, we can certainly do it. It turned out the U was algebraic because the degree of M over L is finite, and so anything in there has to be an algebraic element. And we broke this down thusly. We had L prime M prime was equal to which was and so we were done. So this wrapped it up. Oh, last time, if M was not, well, strictly contained LU. And so what we're left with here is, so to finish, assume that M is equal to LU. So that is, when we take this element of M that's not an L, and you join L with this element, you get all of M. So we'll assume this and show the result whole. Okay. And the way we're going to do this is we're going to construct a one-to-one map from a one-to-one map from a set of left cosets of M prime and L prime. Left cosets of M prime and L prime to the set of distinct roots of F and L. Let me observe that the cardinality. So this set right here is, it could be no more than the degree of the polynomial F, right? So how are we going to construct this one-to-one map? So we're going to let Cal M prime be one of our set left cosets of M prime and L. And let sigma be in the Galois group of F over M. Now remember, this is an automorphism of F that fixes M. And that's connected to M prime, right? Because M prime is the set of elements in the Galois group that fix M, right? Since U is in M, then if we look at tau sigma U, this should be tau U, right? Why is this? Because if sigma is in the Galois group of F over M, U is in M, the sigma of U equals U. So that's tau U. And so what's the upshot? This means that every element of this coset of this coset has the same effect on U. Takes you to tau U. Right? Because an element of this coset is of the form tau times sigma, where sigma is in the Galois group of F over M, and we've seen that tau, it'll have the same effect as tau does, right? So this entire coset has the same action on U. And this allows us, this observation allows us to find the map we're looking for. So what we're trying to do is we're trying to go from the set S of these left cosets to the set of distinct roots. And how's this going to work? We're going to define a map, let's call it something, F, S to T. And we'll see a typical element of S looks like tau M prime. And where do you suppose I should take this? Well, remember, U is a root of polynomial, so how about this? So read what this coset is, take a coset representative and apply it to U, right? This is well defined. As every automorphism in the coset tau and prime has the same effect. On U. And also note, tau fixes the base field K. So tau of U is a root of F. Oh, and I apologize. Let me call this fancy F, right? As opposed to just polynomial F. Okay. So everybody believed this goes where it's supposed to go. It goes to the roots, and that it's well defined. Now, I need this to be 1-to-1, right? Because the conclusion of my theorem is I want this set of left coset, or the index of M prime and L prime to be less than or equal to the degree extension M over L, right? So I need this to be 1-to-1. Now suppose, 1-to-1, suppose that suppose tau and tau naught u are both the same thing. Right, so suppose you have two cosets, tau n prime and tau naught n prime. Suppose they go to the same place. I want to show that, of course, the same. This means that tau naught inverse tau u is equal to u. Right? So tau inverse, or I'm sorry, yeah, tau inverse tau fixes why does it fix all of them? All it did was fix u. But remember, we're in the case that m is all of L u. And so if it fixes this, it's going to fix everything. That means that if this fixes all of them, then this is in fact in M prime. Therefore, tau M prime, tau naught. Because this thing right here is in M prime, so that means that those two cosets are the same. So fancy that is 1-to-1, and hence we get the inequality that we want. That is L prime. Well, the index here plus than or equal. Any questions on that? Okay, I'm gonna have two more little lemmas here that I'm gonna kind of skip over a little bit as far as the proof goes. And you'll perhaps see why. First, we have lemma 8 to 11, which is kind of the other direction of this, if you will. And for this one, we have K and FB fields. And H, and N, and then the Galois group, the length over K. If you have a subgroup of H index that's finite, so this time, instead of starting with fields, I'll start with groups. If I have a subgroup of H finite index, then no surprise here, H prime or J prime, the degree of H prime over J prime is less than or equal to this index. The proof of this is very similar to the previous, and so I encourage you to give that a whirl. I'm also going to leave this one for an exercise, but if you believe this one and the previous one, you can put this together to get this one right here. So the previous two limits are useful in this one. Lemma 8.2.12. In this situation, we have our tower of fields. Okay. Yes,
What does M used in?
I did, and I'm sure it's just a typo. It does, you don't really need it. All you really need is H is a subgroup of the Galois group, and J is just some subgroup of that. That's all you need. I think I did it more correctly here. If you have K, M, F, and this time I think I wrote what I meant to do here. See, go ahead and change the thing here. Yeah, so I think yeah, that's what I meant to write in the first one anyway. So number A, if L is closed, and recall what needs to be closed is L is equal to, L is always contained in its double prime, but it's equal to its double prime. And the index, the degree then M is closed. And L prime M prime okay, so if the field is closed and M is a bigger field that's a finite degree over it, then the bigger field is closed and you get equality for the index versus the degree of the extension. As you might guess, B is similar. If H is closed and J is not too big, that is the degree of the index of H and J is finite, then J is also closed. And H prime, J prime. And C if F is finite dimensional in Galois with K, Galois, okay, then all intermediate fields and all subgroups are closed. And subgroups of Galois group F over K are closed. And in particular, the order of the Galois group of F over K is equal to the degree. Notice that C follows from these two here, and these two here can be bootstrapped from our previous two limits. Because if you have a finite dimensional Galois, just look at this right here and see what you get. Okay, any questions? Let me point out that we've now done almost everything in our statement of fundamental theorem of Galois theory. If you look back at it, what's really the missing piece of the puzzle that we have at this point is that statement about the normality, right? And you know, so normal subgroups correspondent to well, we're going to see what this correspond to directly. I need to develop a little bit more kind of terminology for us to tackle the rest of this. So in dealing with the second statement, let me give you the following definition. So suppose we have A and E and F fields and sigma and Galois group of F. Number one, we say, well, let me do something. We say that number one, E is, yeah, no, I tried that too. I'll bring the sledgehammer tomorrow. E is stable. Yeah. Well, anybody want to take a guess as to what maybe an appropriate definition for a stable intermediate field extension is?
Well, there are Galois.
Right, you want it to, you don't want it to be pushed anywhere else, right? So we'll say that we don't want it to be fixed on E. That's too much. That's asking. But what we can do is, right, so E is like Las Vegas, right? What happens in E stays in E,
So it's
right?
almost like invariance kind of thing going on.
Oh, yeah, it's like invariant, right? But yeah, here's the dangerous thing. This doesn't mean that sigma E is E for every E and E. It just means, you know, it might act like a bit of a washing machine and turn some things around, but everything in E stays in it. And really be stable. I want this to be true for everything in Galois, of course. And number two, tau. Okay, so suppose you have tau. This is an automorphism of E that fixes K. It's not the automorphism of well, it's a priori, it's a automorphism of E that fixes K. When we say this is extendable, yeah. Huh. Okay, so I've got an automorphism on the little field. Right, so it does its magic with the arrows and the fireworks and so forth. What do you suppose it means to be extendable? Right, extendable means that
Construct an automorphism of the
so there's some bigger, by the way, nobody says that this extension has to be unique, right? If I walk up to you on the street and give you an automorphism of E, there might be several thing. Or actually, if it's not extendable, there might be none. I mean, F might be so ugly that you can't extend it. Notice that. Let me make a note. This is for. Suppose tau is extendable. Say to suppose, just for the sake of argument, that you can extend tau to some automorphism of F, then you look at sigma acting only on E, this is the same thing as tau acting on E, which is the same name. So E is stable relative to sigma. I remember to be stable, you really have to, this has to be respected for everything in Galois, but it's stable relative to that one. Well, okay, everybody kind of okay with what's going on there? Okay, so let's get up this next lemma here. This is kind of fun. Let's let K inside E inside F be fields. Fields. If E is stable, so this is a stable intermediate extension, then E prime, which is what?
Or
E prime is everything that's E prime is everything in the Galois group that fixes the Galois group level that fixes E. So this is actually all the automorphs that fix E. This is normal. So if you have a stable intermediate extension, that means that it's the Galois group F over that extension has to be a normal subgroup of Galois group F over K. And if, on the other hand, H is a normal subgroup of the Galois. So, on the other hand, if you just happen to find some normal subgroup of the Galois group, then H prime is stable. So let's prove this. A first. So we know that E is stable. We want to show that the Galois group of F over E is normal in the entire Galois group. So let's let U be an element of E. We'll let sigma be in Galois group of F over K. And this letter I struggle with being the Galois group of F over E. Right? Okay. So we need to show that, um, really doesn't. I show that, for this to be normal, I've got to show that any conjugate in Galois, okay, works. And so to this end, it's clear, isn't it, that this is an automorphism because all of these are automorphisms of F, right? And so the inverse, etc. So really, all we have to do is show that this fixes everything in E, right? So consider now I want to show that this actually fixes. Yes.
Sigma u is in E, right? Because
That is correct.
E is stable, so tornado on sigma u is sigma u, so that's u.
Mhm. So this bit is in E because of the fact that E is stable. Correct? So because remember, this little tornado dude is in the Galois group over E, so it fixes everything in E. Since this is in E, it's got to be fixed. So this is sigma inverse, sigma u, which is u. So, how about part B? For part B, let's let sigma be in the Galois group and V be in H prime. H, and remember, H is a normal subgroup of the Galois group, and H prime is, of course, a field, so V is in there. We wish to show. We need to show the sigma V is also in H prime. Because of course the claim is this thing is a field and it's stable, so when I hit this with any element of the Galois group, it's still in there. Right? Let me retranslate this. So need to show that for all tomato and H, that right. Why is this? Because what does it mean for this to be in H prime? It means that, what else? Right, to be in H prime, you have to be fixed by everything in H. And so equivalently, we show the statement right here. We, to show that this thing is actually in H, we just need to show that it is, fixed by that little tornado guy that's in H. Now we have that H is normal. So we have sigma inverse in H. All right, by the normality of the H. And hence, we have that right there, and this gives us what we want. Composing both sides of sigma, we get and that'll do it for part B. Okay, any questions? Okay, so this is an important piece. If E is stable, then its prime is normal, right? And we've already gotten well, this is a little bit more general than we need, but in the purposes of fundamental theorem, Galois theory, we've got the intermediate fields and the intermediate groups are closed. And if you have a normal subgroup, then it corresponds to a stable intermediate extension. So, if F is Galois over K and E is stable, then E is Galois over K. And E is a stable intermediate extension. So E lives between K and F and it's stable, then E is Galois over K. So if you've got something stable in the middle, then it has to be Galois. And I'm going to use my favorite characterization of Galois. Remember, if you look at the group of automorphisms of E, the big field has to be K. But I'm going to use the characterization to show it's Galois. All I have to do is show that if you have anything in E that doesn't live in K, then there's some automorphism that moves it. Right. I like that characterization, Galois. So let's suppose that we have E not in K. I need to find something that that moves it. Well, so I know that there's a sigma in the Galois group. Such that sigma of U because I know that F over K is Galois, E is an element that's in F and not in K, so there's some sigma that moves it, right? Notice that when I restrict this, note, and this is a subtle point, but I think it's important. Oops. So just take whatever this automorphism is that moved U and restrict it down to E. I claim that this restriction is actually an automorphism. It certainly fixes K, right? Why is it an automorphism? Because E is stable. So this is why stability is important, because if he wasn't stable, then what could happen is what could happen is you could have this automorphism that restricts down to E, push everything over into sigma. Right? But that can't happen because E is stable. So everything in E stays in E. So you can't have this situation. That's a subtle point that when you restrict it, it's an automorphism precisely because everything in E stays in E. Right? And now that we've got that, well, we're done. Sigma restricted to E of U is not equal to E. So E is Galois. Okay, any questions? Yes.
Could it happen if, the degree is not finite, that sigma of E is properly contained in E, and then maybe sigma restricted to E is not an automorphism, but like just a injection?
So the question is, if I'm interpreting this right, let me make sure that I am. So suppose that and you take sigma in Galois group of F over K, and you look at sigma restricted to and get some intermediate field, which I will take the liberty of either of these may or may not be finite. Now you take this automorphism and you restrict it down to E. In your question, are you assuming it's stable?
Yeah, because stable, we don't require equality, and equality will follow if it's a finite degree, because you can make like a vector space dimension argument.
That's right.
But maybe it follows because, F over K is Galois, you can't have it like inject into a strictly smaller field, but, it's maybe.
Right, it's certainly true if E is like finite over K, for example. I guess the easiest thing to look at is K X. If you have an automorphism, it's 1-to-1, push it into.
Like in a transcendental extension, you know, like Q join pi squared is isomorphic to Q join pi, but they're the containment is strict, but it's not a Galois extension, so it fails
Yeah,
that
so
criteria.
if you restrict your automorphism E, I would think that if you loosen some of these, you could probably do this, right? Because you could do something like, so I'm just kind of speaking on my feet now, so I'll think about this, but for example, it occurs to me that you could do something really weird by taking, say, the rational numbers and sticking on infinitely many polynomial variables. So now you've got like this infinite size transcendental function, and you can have some kind of map of sets that, you know, some strange one-to-one map from one to the other, and you can get some field where, you know, right, whenever you have an automorphism in a big field, it's going to induce, it's going, so, well, all these maps of fields are going to be one-to-one, right? It occurs to me that you might be able to do something like that, if you untie enough of these assumptions. But let me think, maybe I can give you, if I remember to do it, I might be able to give you a concrete example next time. So, and if I don't remember to pick on me, but that's fine. So you give me something to do. Lemma 8.216. So I'll give this lemma, and you guys can put this in your pipe, we'll smoke it, and then we'll talk about it. Monday, let K in inside E inside FB fields. K inside F inside EB fields. If E is algebraic and Galois over K. So this is kind of the other side of that previous lemma that we had. If E is algebraic and Galois over K, then E is stable. And we will pick it up there next time. Don't forget there's a math club today, and I know you all are graduate students, well, with exception on set of measure 0. But the math club talk today might be of interest to you, right? The data science stuff, because number one, if you encounter other students, you might be able to tell them about it. Undergraduates ask you things like this. If you're ever going to be in academia or if somebody asks you about this stuff, it's good. And number two, sometimes people in math are looking for a side hustle. So even if you're kind of a committed graduate student, this might be interesting for you as well. So I hope to see you there, and y'all have a good weekend.